Could be a Harry Potter scarf, maybe. Probably. So, anybody have any questions about anything we covered on Tuesday? Nope. All right. I think this is the same group we had. All right. Nope. I don't see any different faces. So, well, I don't know. We'll give it a little bit longer and then I'll do attendance just so everybody gets credit for showing up. All right. Well, I have started working on your first homework assignment. It'll be due next Thursday. I'm going to finish it tonight when I get home. Put some more questions on there from Chapter 3. There are going to be, I'm not sure how it's going to work because this is my first time putting together quizzes of this sort through D2L. So some of them are going to be multiple choice, there's going to be some true-false. Unfortunately, with a lot of math problems, there's one of two ways to do it. It's either I give you 4 answers for multiple choice that are variants of errors that I think that you might make, or I just leave you with the space to let you fill in the number that you think is the right answer. Now, anytime that there's going to be a short answer like that, so if there's anything on the quiz that's not either true, false, or multiple choice or matching, in other words, if there is possibility that your answer might be correct but might not be auto-graded as correct, right? So I'm going to try and come up with things like really common alternative answer type stuff for some of those, like put in your mathematical answer here. But I'm just telling you that D2L is going to grade it for you, or at least give you a grade. It will try to auto-grade it. If there are things like that, if you go back and look and you got those wrong, I will go in and manually double check those to make sure that you didn't put an answer in there that is technically correct and I just didn't think of it to tell the machine first, right? So, so that's the way that's going to work.
Just to clarify, are you talking about homework?
Homework, yes.
But it's a quiz? Like the homework is a quiz?
The homework is a quiz.
Okay.
That you will do online, yes.
And
so,
it's like timed like a test?
No.
Okay.
No. It's submit once, so it's not like do it as many times until you get an A. But it is, get together with friends, work on it, whatever, submit one set of thing. Okay. So it's a quiz that you can open as many times as you want, but that's because on D2L, everything is a quiz. It's either a quiz or a survey, and since I need you to be graded, it can't be a survey. So even the exams will be quizzes, they'll just be big ones that actually do cut you off.
Okay. Are the quizzes like the exams when it comes to questioning, like my question will be different than her question?
No.
Okay.
Homeworks, okay, it's going to be a quiz, but it's the homework. And it's going to be titled homework number 1, homework week 1, all right? So when it goes live, which should happen tomorrow morning, you'll see it, you'll click on it, you can open it up, you can do it. It will be due next Thursday. You'll have as many times as you want to take a look at it between now and then, check your answers, whatever, what have you, maybe work with friends. This is homework. It is a 1/5 of your grade, a little bit less since I'm going to give you one for free as long as you do all of them, right? So I would advise you to double check things, right? Like not necessarily double check them with me in class because I'm not going to work through your homework in class. We can work through examples related to them, but you can check with friends, study buddies, whatever, because there's no reason why you shouldn't be able to get pretty much 100% on all of these homework questions, right? Theoretically, or at least close to it. Like obviously there's the, I'm quite confident of this answer even though I am wrongness type of thing. So that might still catch you every now and again. But one would hope that homework would be a little bit of grade padding as long as you take the time to make sure that you understand the concepts. Okay? But it'll be on D2L. Should go live tomorrow morning. If you have the app that we discussed last time, it will likely give you a ping to let you know that an assignment has gone live. I did activate a discussion thread so that someone, and I mentioned the Pulse app, but I could not give full directions to it. If someone else would like to give directions to how to find it on the App Store or the Google Play Store, in that discussion thread, feel free. If you have other links that you would really love to show or to give, in fact, let me see if I can. Does the audio work on this? Mm-hmm. Yeah, because I mean they do like, oh, I don't know. Adam song? No, that's dumb. All right, I'll find it later and link it. I just had it on my phone like a day ago because I've listened to it, and it's a really neat little chemistry, really nerdy chemistry song. Yeah.
I do actually have a question about some stuff we learned on Tuesday.
Okay, fire away.
So I was working through some of the practice problems, and I noticed that when I got to my answer with significant figures, unless it's an exact number or an exact figure, should we always be answering in significant figures like that? Does that make sense?
Yes, it's a good question. What I will tell you is, with respect to the homework, and I think I'm probably going to try and do this on the test too, if I'm going to require you to answer in significant figures, I will tell you so.
Okay.
So, with accounting for or with significant figures type of thing. Some of the questions are it's going to be obvious. For example, I can give you a preview because it should be obvious. One of the questions on the homework is going to be round this number off to 3 significant figures, right? So obviously there I'm asking for significant figures. If I want significant figures, I'm going to ask for it. Now, I will tell you that, especially on those like fill in your answer type of answers, especially once we get a little bit deeper into the semester, I'm probably going to ask for it, simply because it's easier for me to tell the computer to look for a number at 3 significant figures, or a number that accounts for significant figures than it is for me to input like all 10 possible decimal places that you might have typed in. Because from a computer's perspective, 3.14 is a different answer than 3.1415.
Yeah.
Right? So, but I'm not going to try and screw you up by not mentioning it one way or the other.
Okay. It was more so like working through the conversions. There was a couple that I just couldn't figure out where you got your answer, and then I realized it was because you...
rounding significant
yes,
figures.
Yes.
Right.
Okay.
And that's going to be especially true in the conversions. Remember, if you ever convert between metric and American, significant figures matter.
That just should always be...
With the one exception of what? What's the one conversion that doesn't, where it's exact?
Equalities.
Well, they're all equalities. What's the one conversion between American and SI or metric that is still exact on both cases and therefore does not affect significant figures?
Inches to 2.24.
Inches to centimeters, yes. 1 inch equals 2.54 centimeters. That is exact. All of the other ones, the significant figures, which are always from the American measurement, like 2.20 pounds, so 3 significant figures for anything with pounds, that type of thing. Yes, we can argue that rabbit hole. We're going to all agree that it's exact for now. As long as we all agree on what is and is not exact, we can all do math the same way. And that's the way math works. Does that answer your question? Okay. Like I said, I'm not going to try and trip you if the point of the question is to understand significant figures, then it will be obvious. Okay? All right. Anything else? Okay. Let's talk about chapter 3, shall we? So, 3.1, classification of matter. Learning goal here. Examples of matter as pure substances or mixtures. So here we have a copper penny and we're cheating. But let's just say that copper pennies are pure copper for purposes of this illustration. So here we have a 3-dimensional spatial model of what that copper might look like, with a whole bunch of copper atoms lined up into a matrix or crystalline structure. This is an element that happens to also be a pure element, a pure substance, because it is made out of entirely copper. Once again, by way of our oversimplified example. There's another minor rant about coppers. Oh, I never gave you the rant about degrees of wrongness, did I? There's a minor rant about pennies. I hate pennies. Pennies are worth, it costs more to make a penny than the value of a penny. In the US fiscal system, we should get rid of pennies and probably nickels while we're at it and just throw it all out and just round everything to the dime. Because, when you could buy something significant with a penny, then sure, but you can buy nothing significant with a penny. So, how many of you reach down and grab pennies when you see them on the street? Be honest. We got one hand over here. 2, 3, maybe 4-ish. Does it matter if it's heads or tails? Is it just the whole luck thing?
No, it's because you can buy people's thoughts.
Because you can what?
A penny for your thoughts.
Oh, penny for your thoughts. That's
an economy that never changes.
I see. Most thoughts are also free, or if I needed to require you to pay me for them, I would charge you much more than a penny. But most of my pennies I end up leaving in like the somebody else needs a penny later jar type of thing at gas stations or whatever. So yeah, pure substances, elements. Elements are composed, or a pure substance is composed of one element. We can classify matter, which is what we're talking about here, as anything that has mass and occupies space. Pretty much anything that you are going to be directly interacting with is matter. Now, do you directly interact with something other than matter? Is that sort of a trick question? You also directly interact with energy. Specifically, there is a type of energy that you are directly at least absorbing, if not interacting with. No, that's not fair. You're giving some of it off too. You're converting it from one form to another. What am I talking about? Electromagnetic energy, otherwise known as light. We'll get to that later. I don't think today, though. So, anyway, here we go. Light being this interesting thing that sort of that doesn't have mass, and yet also is affected by gravity, which affects matter, whatever. So, water, wood, plastic bags, the table in front of you, the pencil, the computer, the paper, the air that you are breathing has mass, is made of matter just as much as the table and the ground beneath you and the clothing that you are wearing and the body that you are made of. Your body is composed of elements. We can classify all of that matter based on its composition. We've got pure substances here. These things have fixed or definite compositions, so that particular substance doesn't change. We have mixtures that are combinations of more than one pure substance. So here we have a lovely flow chart. So we start with matter up at the top. We've got pure substances that can either be elements or compounds. What's the difference between an element and a compound? Because we haven't been told quite specifically in a slide yet, so you don't have anything to quote. Unless, of course, you actually already know this.
An element is homogeneous. A compound is made up of one or more elements.
There you go. An element, you could say homogeneous or is a monomixture. It is not a mixture, it's the same thing. An element is one thing that is, you can put a tiny little asterisk next to this, all exactly the same. Because we're going to talk about later about how different aspects of elements are not actually all exactly the same. But for now, until we get there, we can consider them to be all exactly the same. So, copper penny made entirely out of copper. One element, a pure mixture, right? Compounds like water, and the vast majority of everything else you interact with are compounds. They are made up of more than one type of element. So what are the two elements that compose up water? Hydrogen and oxygen. Right, pretty simple stuff. Then we get, instead of pure substances, we get mixtures. So what's the difference between this homogeneous mixture of brass and this, otherwise you could say also homogeneous mixture of water? Because, I mean, water is always going to come as H2O, right? I'm sort of lying to you. Once again, this sounded like, well, how much are we oversimplifying here? One could argue, well, technically water will sometimes automatically subdivide into a hydrogen and hydroxyl ion of equal proportions, depending upon the pH. We can get deeper into that if you wanted to. We don't need to right now. But generally, this is a homogeneous mixture, but we call this a compound. What's the difference between this homogeneous mixture that we call a mixture instead? Well, the brass and the copper, even though we've drawn these in this beautiful little matrix that we have here, brass and copper do not actually form this necessarily equal, copper and zinc do not form this equal ratio and perfect matrix. But it is a homogeneous in as much as that when you look at this tuba, Sure, let's call it a tuba. I don't have a person for reference of size here. Let's call this a tuba. When you look at that, there aren't going to be spots of it. We're having a minor earthquake here. There aren't going to be spots where it's like, that's obviously where the zinc came in, and then this other bit over here is obviously where the copper comes in. It's all just brass. It's all this even mixture of copper and zinc. But what's the difference between that and some other compounds that we're going to talk about later? Well, for one thing, this mixture of copper and zinc, even though it is homogeneous or has come to an equilibrium with its concentrations, it can be separated from each other via mechanical means if we're really, really careful, but really what we're talking about here is that those things are just hanging out because it's the only way to be. We're going to talk about a compound later called sodium chloride. Do you know, guys know what that is? Salt, right? Sodium chloride is a compound, not a mixture. Why? Because even though sodium and chloride are not covalently bound in the same way that the hydrogen and oxygen are here, if you don't understand what covalently bound is, don't worry, we'll get to it later. Even though hydrogen and oxygen here are holding hands in a semi-permanent manner, sodium and chloride are also reacting to each other. They are associating with each other. The term that I like to use as a metaphor is they are sort of holding hands in a manner that enforces a very specific and universal ratio of sodium to chloride. But when we made this brass tuba, we did not guarantee that there was a 1-to-1 ratio of copper and zinc. We do not guarantee, because of the inherent nature of the atoms, that they will align in this beautifully drawn crystalline matrix. But they will pretty much mix evenly and create a thing we call brass, which we then pound into something we call a tuba. So this is a mixture. And then we have a heterogeneous mixture, which is very poorly illustrated like water and copper. Could you give me a better idea of what a heterogeneous mixture might be that we've actually already discussed?
Alcohol and water.
Alcohol and water, or perhaps an olive oil vinaigrette dressing, right?
Is that ever homogeneous?
Yeah, it's heterogeneous. It is not a homogeneous mixture. By definition, a vinaigrette is not homogeneous because they will desire to separate from each other. Even if you manually mix them, it will never reach homogeneousness. It could reach something close to it for a millisecond or two if you're really, really forceful.
Is there what means it?
It's going to be heterogeneous in that case. So a heterogeneous mixture is multiple compounds put together where they will never achieve any sort of even distribution. If they achieve an even distribution, then what would we call it? Homogeneous. Which, copper pennies inside a glass of water, that's never going to happen, right? So, let's talk about pure substances. So can I go back a little bit, or define an element, a type of matter with a fixed or definite composition. An element is what we use to define that smallest aspect of the composition of that pure substance. So a pure substance is composed of one atom. If it is composed of only one atom, then that is the element that we are describing. You can't have a pure substance composed of a compound, which is two or more elements, therefore two or more types of atoms. So when we're talking about very simplistic chemistry, you can use the word element and atom not quite, but almost interchangeably. An element describes something that we can collect as atoms. A compound is composed of two or more elements, which means it's composed of two or more different atoms, different types of atoms. The reason why they are not exactly different is because you can have a soda can made out of quote-unquote pure aluminum. How many atoms are involved in the composition of that soda can? A bunch. Way more than one. But all of those atoms are, once again with that tiny little star next to it, all the same thing. They're all just aluminum, which means they all have similar chemical, if not exactly the same chemical properties. That is, in fact, what makes an element, is that it has all atoms of the same element have the same chemical properties. you're not sure what I mean by chemical properties, don't worry. We'll define what those are. You can have a pure substance made up of copper, which we abbreviate Cu. You could have it made up of lead, which we abbreviate Pb. Made up of aluminum, which we abbreviate Al. What do you notice about all three of those abbreviations? What's the first letter? Always uppercase, and the second letter is always lowercase. Not all elemental abbreviations have two letters. Without looking at the periodic table over there, name one that does not. It has just one letter. Oxygen, nitrogen. Anything else? Carbon.
Things that end in M.
Interesting. Hydrogen, yes. So, we're going to talk about the periodic table of elements extensively, but not quite yet. So compounds are those that consist of more than one element. H2O2 is hydrogen peroxide. Table salt, sodium chloride. Why is it that our abbreviations always have capital or lowercase letters? If you were to see something like H and O next to each other, would you assume that that is the element homerium? If it was a capital H and a capital O? No. Why? Because they're both capitals, right? So you would know that that was hydrogen and oxygen, that we were describing a molecule that somehow contained only one hydrogen and only one oxygen. It is not impossible. In fact, those particular molecules are quite common, especially in aqueous solutions. We call that the hydroxyl ion. Usually we would represent it as HO minus, but we'll get to that much later. NaCl, you know that that's two different atoms. How? Because the capital N and the lowercase a tells you that's one element, right? And the capital C, lowercase l, tells you it's the next. We're getting a little bit beyond the slides, but I'm wanting to make sure that we're all on the same page when it comes to chemistry, right? We have to speak the same language if we're going to understand each other as we move along. Sugar, C12H22O11. That's cheating. This is describing table sugar, which is actually sucrose and glucose, or excuse me, which is sucrose, which is glucose and fructose, covalently bound via an ester bond. And you followed that. You will, hopefully that will be easy. If it isn't already easy, by the end of the semester that should be easy. And then of course we have water, H2O. Have you guys ever signed those petitions about oxygen dihydride and how dangerous it is and how we should regulate it and ban it?
Hydrogen monoxide.
Yeah, hydrogen monoxide, yeah, oxygen dihydride. Yeah, so, you know, how it's deadly in high concentrations and has killed people and interesting things like that. It's just an illustration of how science ignorance is a punchline. Because that's water. And yeah, water can kill you, but you also have to have it, right? How long can you go without a drink of water before you start suffering severe effects up to and including death?
3 days.
3 days. How long can you go without food?
3 months.
Yeah, a week or two, depending on where you're starting from, sort of. But yeah, 3 days of no water, you're in pretty bad shape.
Surprised we disagree.
I'm gonna set that on a shelf.
I'm on 24 days.
So, there's a guy over in India, was it India? That swears that he lives on nothing except the energy from the atmosphere and the water from the morning dew. I don't believe him either. There's also a guy who swears he's never pooped in his life. I don't believe him. There's a guy who says he's never showered. That I can buy. Anyway, what's the difference between H2O2 and H2O? Well, one has an extra number, right? H2O is water. H2O2, what's it got an extra of? It has an extra oxygen atom. But that shouldn't make a big difference, right? I mean, you should be able to use these things relatively interchangeably, right? Because everyone knows it's perfectly safe to drink hydrogen peroxide, right? Don't ever drink hydrogen peroxide. That's one of those, like, you gotta be careful. That extra oxygen atom that's in hydrogen peroxide makes a really big difference. But it is that extra oxygen atom, and therefore the change in shape that is required in order to make that stable molecule, that gives that chemical its properties. There is absolutely nothing that separates this water molecule from that sugar molecule. They are both made out of the same physical things, i.e. atoms. And yet the order and chemical properties of the atoms that make them up will give them very, very different properties. In the same way that if I make a teddy bear out of lead, my children will not love it. But if I make it out of cotton, they might. Still not a guarantee. Compounds contain more than one element. Table salt is made out of sodium chloride, but we can separate that sodium chloride compound into sodium metals and chlorine gas. That sodium metal is a really fun thing to throw into water later. It's rather explosive. Exothermic reaction. So this process is deceptively simple on this slide. Salt is not that easy to separate into sodium metals and chlorine gas, but on a daily basis you do chemically separate table salt by doing what?
In water.
By dissolving it in water. Whether you realize it or not, when you're adding your salt to your food, what happens either the moment it touches your food, or if not, if it's really dry food, the moment your food touches your tongue, that salt will dissolve in water and break down into sodium and chlorine, except both in aqueous form. So there won't be any tiny explosions on your tongue. Thank you. Mixtures can be separated. Here we are straining a mixture of water and pasta. Metaphorically applicable. Chemically not so much, but you know, it's hard to describe chemical separation or physical separation other than this. So here we have a mixture, or what was once a mixture, pasta and water. We can separate that mechanically by running that through a strainer. The water goes through. The pasta, one would hope, does not. We can do the same thing very similarly with chemicals. We can separate them in any number of means. Here we are separating with a filter. This is pretty much exactly the same thing as the pasta and water, with the exception of a much smaller pore size on our colander. And then here we have a separation of different chemicals based on how they move up this paper in liquid chromatography, which is really neat. The way things move in a dissolved solution in relation to how much they don't want to move as they are interacting with the binding paper that is moving up. So if you're something that doesn't care about sticking to this paper, you will climb this paper at the same rate that the water or alcohol solution down here is climbing the paper, because you're just dissolved in the liquid, moving right along with it. But if there are any chemical properties that make you want to grab onto this paper, it's like the difference between trying to take a child to the bathroom for a bath at night when they want to take a bath. They're very eager to go with you. But if they don't, they will reach out and grab every possible thing they can to slow you down. Well, the children that like baths are moving with the solvent. The children that don't like baths are holding on to the paper. And if we take this metaphor and apply it to chemistry, what is it about those chemicals that make them not like baths? It has to have something to do with differences in their chemical makeup. A water molecule does not just decide that it doesn't like oil molecules one day. It always doesn't like oil molecules. And so if there is a difference in how those ingredients react to that paper, it is because of a difference in which elements are combined in which way to make up that compound. Because those physical differences have to come from a difference in how that compound is made. Even if it's made from exactly the same atoms, if we organize them in a different way, we can have a compound with a different physical property. Homogeneous mixtures, relatively, if not in fact by definition, uniform throughout the sample. We cannot tell which parts are where. If we could, it would not be uniform. Once again, brass is not an even commixture between copper and zinc, but it looks like it in the picture. I'm only telling you this because I actually know a little bit of metallurgy and care. Most people wouldn't care, and so it's just like, look, it's the thing. So, you know, color these balls differently, and you've got exactly the same picture. They give us some sodium chloride because it just makes for a nice graphic. This is where the art department in science textbooks really needs to get a better science education. But it works. How about something else as a homogeneous breathing mixture? So the scuba mixtures that you might use when you go scuba diving, nitrox, a homogeneous mixture between oxygen and nitrogen, heliox, oxygen and helium, which that would have to leave you, A, give you a headache, and B, leave you talking really weird when you come back up. I don't know, I don't scuba dive. This is another one of those hobbies that I would love to pick up, but I need another hobby like I need another hole in my head, and it's not an inexpensive hobby, so it's never going to happen. Unless, of course, I decide to take another cruise, and then I might figure it out so I could go scuba diving on a you know, coral reef before they all die. Trimex, oxygen, helium, and nitrogen. Why would you want something that's oxygen and nitrogen? If you're scuba diving, why wouldn't you want just pure oxygen? There's a myriad of reasons. One, pure oxygen is really dangerous. Transport and storage. What's the primary component of the atmosphere that you're breathing right now?
Nitrogen.
Nitrogen. Upwards of 70% nitrogen. So why not, if you're going to make a pure gas that you're shoving into a tank so that you can breathe it underwater, why not make something that's kind of like what you're breathing now? A heterogeneous mixture is the example given with the pennies in water. Varies from one part of the mixture to another. And the different parts of the mixture are visible in some way, shape, or form. Once again, perhaps a better example of a heterogeneous mixture would be a vinaigrette dressing, right? The oil with the water. They do not like to mix. You can force them to, but you can still see the divisions. Even with a really vigorous shake, you can see the little oil droplets in the water. Heterogeneous. All right. Let's talk about properties of matter. Silica are the gray ones, oxygen are the little red ones, and here's a nice little space film model to give you an example. And I honestly don't know if that's the accurate example, but it might be. But once again, I don't know how much I trust the art department, of what it takes to make an amethyst crystal. We can take these same two atoms and organize them in a myriad of different ways to make a myriad of different, sometimes we call them elements, but that's because amateur geologists and rock collectors are inappropriately using scientific terms. What's a more appropriate term to describe this? Perhaps a mineral? Did you have another one? No? If you go to natural history museums, they'll give you all sorts of different calcites, fluorites, things like that, the description for these minerals. And the differences that you see in the crystalline structures have everything to do with the way in which those atoms organize themselves to form a crystal. Different crystals in different shapes have very different properties, even if they're made out of the exact same thing. Is there a difference between the lead? How many of you guys are actually using a pencil right now? Okay, a handful of you. Is there a difference between the lead in your pencil and the lead in the diamond ring or earring that you may or may not be wearing or may not own?
Yes.
Sure, sort of. They're both made of carbon. So, in that respect, no, they're exactly the same. But that does not mean that you should attempt to trade your pencils for diamonds. No one will allow you to. The shape of the matrix is very, very different, but they're both made of carbon. Solids. Physical state of matter. It can come as a solid. It has a defined shape with a definite volume. Solids are held together by very strong attractive forces between the atoms that make them up. Now there are some attractive forces that are stronger than others. By way of example, the stuff that holds this amethyst crystal together is much stronger than the stuff that holds together a chunk of salt. Take this amethyst and drop it in water. What's it going to do? Get wet. Take a brick of salt and drop it in water. What's it going to do? Disappear. Dissolve. We'll talk about why later. Particles are arranged in a rigid pattern and therefore can only vibrate slowly in fixed positions. True or false, all atoms are vibrating at all times?
True. Absolute zero.
Right. We were unaware of any that actually exist at absolute zero. Finding them, but it is a theoretical state. So yes, all atoms are vibrating in some manner. If they are in a solid, they are locked into a crystalline structure of some sort, and therefore their vibration is limited. Now, by definition, that means that there should be another description of matter where these particles are not locked into a rigid pattern and therefore can vibrate in any number of directions. What would we call that physical state of matter? A liquid. Liquids have a definite volume, just like solids do. But they do not have a definite shape. Why is that? Because their atoms are held together via more intermediate bonds, if there are any bonds at all, and therefore their atoms can shift around and over and on top of and under each other to occupy whatever shape it is that the container holding them currently partakes. Which is why water in a glass will occupy whatever shape the glass is, even if it's really one of those really, really weird decorative glasses. On the subject of glass, okay, I'm going to have to cheat a little bit here to give perspective, but if you go back, if you find a house that was built in the 1800s, and you look at the glass that is in the windows of that house, assuming that they have not been changed to more modern mixtures, but would you call the glass in those windows solids or liquids?
Liquid. Amorphous.
They're liquid. And yet they've been in a house since the 1800s, occupying the same shape, right? Well, that's where it's actually kind of lying. They're not occupying the same shape. If you go back and look at glass that was made a century or two ago, and you look at its shape, it will have slowly, well, let's put it this way. Imagine that you could somehow take water and make it occupy the shape of a window pane, right? With perhaps two other sheets of glass. If you immediately removed that, what would that water do? It would immediately start following in terms of flowing down because of the pull of gravity, right? Well, the glass in those windows has been doing that. It's just been doing that very slowly, so much so that you might not notice. But you could pull out a little ruler, a little caliper, and measure the top of the glass and the bottom of the glass, and guess what? The bottom would be thicker. It's a liquid. We use it as a solid. We treat it like a solid. Because it is so viscous, because it moves so slowly. Rubber's the same way. My kid has some silly putty, my daughter. She can pull it out and make it take whatever shape she likes, which should tell you something, right? Solids occupy a definite shape. She can take that silly putty out and make it take whatever shape she wants, but you put it back in that little egg that it comes in, you let it sit there for an hour, and it doesn't matter what shape it was before, after an hour of being a little egg, it's always going to be a little at the bottom of the egg, occupying the shape of whatever side of the egg it was in. It's liquid. Gases. Indefinite shape, indefinite volume. They're also going to take the shape and volume of the container where they're found. Sort of. I don't like using balloons as examples of containers for gas. Why not? What's the shape of a balloon? What's the volume of that balloon? You could define that, right? Okay, great. Now take the exact same balloon, teleport to the top of, say, the top of the tallest building in Denver. Is that balloon going to have exactly the same shape?
No.
No. Now teleport, you may not notice the difference though. Now teleport up about 5, maybe 30,000 feet. That balloon have the same shape? No. Why not?
It's broken.
Well, one, because you can't teleport. Two, let's not break the metaphor here. It might be popped, yes, at 30,000 feet especially. But what's going to happen to change that balloon? The shape is going to change. Why? Because the shape of that balloon is actually dependent upon more than just the gas that's inside it. It's also dependent upon the gas that's outside it. As you go, these balloons rise up into the air. I guess when you were a kid, you ever done that? When I was like 4, for my 4th grade birthday party, we made a little birthday card for me. We tied like 30 balloons to it and I let it go. 3 weeks later, I got a card back in the mail from whoever it was that found my birthday card, like miles and miles and miles away. It flew up into the air, kept rising higher and higher and higher until the balloon swelled up and popped, and then that birthday card fell to the ground. And someone happened to fall somewhere where someone could find it. And so they wished me a happy belated birthday 2 or 3 weeks after it happened. A total stranger that I'd never ever met in my life. Kind of neat. Gases are kind of special. The particles are very far apart and they move at very high speeds. They have very little attraction to each other. So, here's a table with convenient things about the comparisons between solids, liquids, and gases with respect to their volume, arrangement, interaction, movement, and some examples. Once again, so that you know if you need to look up some properties of matter, you can come back to table 3.1 on slide 18 instead of looking up the last 13 slides, right? If you need a refresher. All right, so those were physical states. What about physical properties? These are things that can be observed or measured without changing the identity of a substance. Because sometimes observing something changes it. So, the shape, the state, boiling and freezing points, the density. Have we talked about density before? Right. The color. These are things that are examples of physical properties. What are those physical properties going to be determined by? What gives a thing its physical properties? Which elements, in what order, make it up? What's the difference between water and hydrogen peroxide? There's some big differences, right? All because of that extra atom of oxygen, which gives it a very different shape, which gives it very different properties. Both are liquids, though, in that particular example. Copper, an element that we've discussed somewhat so far. Reddish-orange color, kind of shiny, especially if you buff it a bit. Excellent conductor of heat and electricity. And you guys have any cooking pans that have copper in them? Especially like the bottom bit, because they're really, really good at conducting heat. There's an interesting thing you can do. I would advise you do this. This is only if you A, have access to copper pipes, or even better, a solid copper tube, which most of you probably don't, because copper is actually one of those, like, if you had one, why haven't you sold it to somebody? That's worth a little bit of money now. But if you had a solid copper tube that you could wrap a dollar bill around, you could take that dollar bill and hold it over a candle, and it would not burn. It would char a bit, but that's actually the charring from the candle burning, not from the dollar burning. Because the copper is so good at wicking away that heat, at sucking the heat, that extra energy from that dollar bill that's being imparted by the burning candle, that the dollar bill will never char. It will not burn, not never. That for a short period of time, that dollar bill will not burn, even though you're exposing it directly to flame. That's how good copper is at wicking away heat, at absorbing and moving heat. Why wouldn't it work so well if it was a hollow copper tube? A lot less copper, there you go. It's solid at 25 degrees, in other words, room temperature. The melting point is 1083 degrees Celsius. The boiling point is 2500. Neither of those two temperatures would you be comfortable at. It'll melt at over 1000 degrees Celsius. It will boil, turn into a gas, just over 2500. A physical change is when we move a thing, an element, a compound, from one physical state to another but we do not change its chemical makeup. Its composition does not change. So the example given here, water exists in 3 different states. It could be as solid as ice, it could be water, or it could be steam. Now this is an oversimplification. And I'm going to tell you this because if you look it up, it's going to be really, really cool. Look up super liquids or hyperliquids. I don't remember if I'm using exactly the right term. The point is that there are more than 3 physical states that water can exist. Each one of those states has a very specific set of properties related to the fact that it is water in that state. But there are more than 3. But I'll give you, the reason why you probably haven't heard of these other things when you look them up is because, well, they're really hard to get to. You have to have specialized equipment to force them into the right temperature and pressure range. But the 3 ways that you can find water easily on an everyday, any day of your life is either as ice, liquid water, or gaseous steam. 3 different physical states. We can change the appearance of a substance without changing its physical state. We can take this gold ingot down here, 100 grams. I don't even want to know what that's like. We could do, there's a homework problem for you. 100 grams converted to ounces, what's the value of an ounce, the current exchange rate for an ounce of gold, and it would be a lot. Gold is heavy. So that 100 grams of gold, that's quite a bit of money. But we could take that 100 grams of, what state is that gold in right now? Solid. It's not a gas and a liquid, right? We could pound it down into that sheet of gold, the gold foil. What state is that gold foil in? Still a solid. Have we made a physical change to it? Yes, but we have not changed its state. We have not changed it from a solid to a liquid, or from solid to a gas, which is possible, by the way. I don't know how easy it would be to do for gold, but it is possible.
$4,200.
$4,200. That right there, 4 grand.
Yeah, it's $42.09 as of today, an ounce.
An ounce. What?
Or gram.
Or gram? Yeah,
An
so
ounce
that'd be
is
a gram.
1,300.
Right, there we go.
I'm buying.
Yeah.
Yeah. That's just nuts. Anyway. All right, so we've talked about physical properties, right? What's in between a physical property and a chemical property? A physical property describes a property related to the state of an element or compound. A chemical property is a property related to the way in which that substance in its current state interacts with the world around it. How it interacts with other substances and what it takes to change it into a new substance. When we have a chemical change, we have converted one or more substances into something new. So we can take a gaseous hydrogen, we can take gaseous oxygen, and with the addition of energy, hopefully in a controlled manner, we can encourage them to go through a chemical change to change into gaseous water. A huge amount of that central fuel tank, when you guys watch the space shuttle go into space, right? Like, the next generation is going to say like, oh yeah, I saw that in a movie once or something, because we're not doing that anymore. But that big, huge central tank, most of the fuel in that big, huge central tank was just hydrogen and oxygen. When it burned, it produced water. Zero emission. Now, the 2 boosters on the side, that's a completely different story. Lots of carbon footprint in there. But that's big central one. A Chemical change is when we are in some way altering the chemical properties of a substance. And the only way to do that is to alter the number, type, and arrangement of the atoms found within it. Because it is the number, type, and arrangement of the atoms in a compound that define its physical and chemical properties. So if we are making a chemical change, if we are changing the chemical properties, then we are changing the number, which atoms, or which order they are in, of the thing that we are talking about. This is one of the reasons why I was so happy to pick up a chemistry course as opposed to a biology course, because biology, which is where I started from, even though my PhD is in chemistry, biology at its heart is simply, in my opinion, the ultimate expression of both chemistry and physics. Because everything you are doing, even right now in this moment, is chemistry. The act of listening to me talk, the act of hopefully remembering what I say or in some way learning something meaningful from it and storing that information in your brain, all of that is chemistry. Because it is the only way that we know how to be. It is the only way that we know how to interact with the world around us is through chemistry. And somehow, through mechanisms we have yet to quite figure out, it is also the way in which you remember who you are, remember who you were, and hope for who you may become. All of that is just chemistry. Forgive me if the word just seems to oversimplify that. I do not mean to. It's an amazing thing, but it's still chemistry. During a chemical change, a new substance has formed that has new composition, new physical properties, new chemical properties. If we take iron nails, put them in a little bit of water, especially salt water, and leave them out, what's going to happen? They're going to rust. Is somebody dancing on the floor above us or something? Or just having minor information? Oh yeah, I bet that's true. So, when that happens, it's not just pure iron in those nails anymore. The iron on the surface of that nail is reacting with oxygen in the water and the air, and it is forming a new compound, iron oxide, otherwise known as rust. By the way, here's a biology joke for you. Do you know why our blood is rusty? Darn it, I ruined it. Do you know why our blood is red? Because it's rusty. What does our blood do? It carries around oxygen, right? What's the central atom that does that? We have a term that we like to use to describe the amount of dissolved oxygen in our blood. That's fine. That's just dissolved oxygen. That's not, well, it's a little bit different, but it's not that much different than the amount of oxygen that's in the lake outside or in the water that's coming out of your tap. So why is it that your blood can carry around so much more oxygen than just pure water? Because you have something in all of your red blood cells whose sole job it is to carry a buttload more oxygen than that. And the thing at the center of each one of those hemoglobin molecules that does the work of that molecule is iron. And what does iron look like when it has oxygen attached to it? We call it rust. It's red. Why is your blood red? Because it's rusty. Interesting sci-fi fact. Any Trekkies in here? Vulcan blood is green. Because according to Gene Roddenberry, guess what's at the center of the oxygen-carrying molecule in Vulcan blood cells? It's not iron, it's the Statue of Liberty. Copper.
Chlorine. Better than chlorine.
Better than chlorine. Why does carbon monoxide kill you? Because carbon monoxide will covalently and permanently attach to the iron at the center of the hemoglobin molecules in your red blood cells. You suffocate when there is plenty of oxygen in the room, because the carbon monoxide will selectively kill, if you will, the function of the thing in your blood that lets it carry more oxygen than just regular pure water. Even if there's plenty of oxygen in the air that you are breathing, you will suffocate from lack of oxygen. iron. That is a reversible chemical reaction. Collects oxygen from your lungs, lets go of it, and gives it to the rest of your body. But that also is just chemistry. Physical and chemical changes. We've described them all. A physical change, water boils to form water vapor. But that's a physical change. Why? What were we when we started? Water. What were we when we're done? Water. But we changed state. That's a physical change. We're still just water, right? But if we take water and add, say, take water and let it fall from the sky through some air that has a whole bunch of sulfur in it because it's up kind of downwind, if you will, from a coal plant. And it picks up that sulfur and it lands as sulfuric acid on the ground. Is that a physical change or a chemical change? Chemical change, because we have taken multiple compounds, combined them into something new with new properties, even though both of them are liquids. So, example of physical changes, example of chemical changes. Did you have a question? No? Okay. Summary of physical changes. Characteristic of a substance or physical property, is it just what the color, what the shape, the odor, size, melting point, density, etc. If we have a physical change, we are changing a physical property that retains the identity. Still water, it's just changing from gaseous to liquid. It's still gold. It's just changing from one solid to another solid, i.e. gold bar to gold leaf. Chemical changes, something that converts from one chemical to another, one substance to another. And the new substances have different chemical properties than the substances that they were to begin with. All right, so we've gotten through two things. We've been here for about an hour. Oh, shoot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're all here. Good. All right. Let's go ahead and take a 10-minute break. We'll pick it up with temperature here. Stretch your legs, do some jumping jacks, get a drink. Some Doritos or something. Wake up. Super important. You just remember chapter 2, whatever the syllabus. The only thing I'll say is that since you weren't here,
yeah,
homework is going to be online.
Yeah.
Which, I mean, it's all in the syllabus, but homework's going to be online.
Where is the syllabus? Because I looked on D2L and I couldn't find it.
There's that introductory page in D2L that says, hey, welcome to class. There's a thing that says, click here.
Oh, okay.
And that's the link to the syllabus.
Okay.
So click there, and there's the syllabus. And so homework's going to be online. It should be posted probably after class every Thursday. It'll be due by the next Thursday's class.
Okay.
It's going to probably be all online. I might have to give you a worksheet once or twice.
Okay.
I don't know, we'll see. And the exams are all going to be online every other week.
Okay.
They will also go live after
Are they on
class on Thursday.
Thursdays?
Not on Thursdays, no. They're going to be online, just like your homework, just bigger.
Okay.
They'll go online. They'll be live Thursday after class, or excuse me, Friday morning, and you will have until Sunday at midnight, so 11:59 p.m. Sunday night, to start it. Once you've started it, you'll have a 2-hour window to finish it.
Oh, so it's not in class?
Correct.
Oh.
I'm not sacrificing an hour every other week to take
I'm not gonna fight you.
Okay.
I'm not
Right,
complaining.
yeah, it's gonna be
I
on.
was just shocked.
Yeah.
Okay,
So it's
awesome.
online, so therefore it's open book, open note, open friend. But it is gonna be a timed test, and it's random block, which means that even if you do have a friend,
You're only asking questions.
right. So you can still sit there and help each other take a test, and that's fine, because then you have to explain why you think the right answer is A, B, C, or D. And if that explanation helps you to finally understand and figure out and maybe even remember that concept, then my job is not to test you, my job is to teach you. So that's why I do it that way.
Okay, awesome.
So, but yes, and then if you forget or miss, the exam will stay open after Sunday, but you lose 10% for whatever grade you get for every day that you were late. So it's not the end of the world if you forget, like, you know, go to bed because you're tired Sunday night and you totally meant to take your test, but then you can take it sometime on Monday and just lose 10%.
Okay, awesome, thank you.
Yes.
That's the whole
Um,
thing.
there will be a discussion post as soon as I get it up with as much of the video as I was able to capture on Tuesday.
Okay, thank
My
you.
battery kept dying.
Okay.
So you're recording this?
I am recording.
With my
You
permission.
can go back, you put Adam up on the big screen.
Yeah, you can capture all of those nefarious things that I'm saying and announce them to the world.
So if
Did you
there
know
are
your file was in
classes
zip
that,
last week?
Did I what?
Did you know your file was in zip last week?
See, you say that because I'm nervous about that. That's like, one of those things where I have to check every time I walk into a room. Like, anyway, yes.
so if we miss a class, we can post.
That's awesome.
It is his intention with my permission, because I used to record my lectures anyway. So, and I would have done that anyway here, but unfortunately all of the technology that I had at my previous institution, in order to allow me to record my lectures, was property of that institution. So when I left, I couldn't take it with me. So I'm fine with the lectures being recorded and being made available for students so that you can catch up, catch the parts that you miss. Unfortunately, even though we are recording our lectures, that does not change the attendance requirements from Columbia College.
So what do you mean required? That's for like if you have financial aid though, right?
Yes.
Because I've had classes in the past where we actually got attendance points, and then I've had other ones where it's just, you have to have a second
Right,
attendance.
yeah, no, not being here is not going to hurt your grade in some manner, other than it might impact how well you pick up the information, but it's not going to inherently hurt you if you are not here. That being said, I am required to keep attendance, and so if there is any attendance-related policy about not being in class, then you may still run afoul of that. So me personally, I wouldn't care, especially since the lectures are online. Theoretically, you could never be in class. You could log in and do your homework every Friday night, and you could log in every other weekend and do your tests every Saturday afternoon, never show up in class and still get an A. Because if you know this information, then you know this information, right? And you just proved it by taking the exact same metrics and rubrics as everybody else who came to class. But the problem is that every institution has different rules about how they incentivize and require students to actually attend the class, and especially with respect to how their personal policies integrate with federal policies. So yes, the main thing is if you're getting any sort of financial aid, the federal government is not kosher with handing out money to people who don't actually go to school to do the thing they said that they were going to do to get the money in the first place.
It's okay, then we'll pay back.
So you can't miss more than 2 weeks like consecutively. So it's like once you miss your third class, your fourth class, you can be dropped.
But that's if you have financial aid though, right?
I
Like
think
for me, it's like.
I think it's Columbia College's policy if you have a C or lower in the class, and then it's like if you have financial aid, it's your policy in general.
Yeah.
Are you familiar with flipped classroom? Pedagogy is just undergoing a massive improvement, especially with our really difficult cram an entire book into 8-week sessions.
Yeah.
The flipped classroom is the teacher records the lecture along with often a screen tracker, so you can draw on the screen and stuff and add narration. And then your job out of class is to watch the lectures. When you come in here, it's all troubleshooting, mastery. I didn't understand this part, and you spend the whole period.
Right. Small group sessions, interactions, working about your homework, doing little things, talking to the teacher about application, and doing the things that you have to already have mastery of the subject before you can even do it. And so it's definitely a intriguing and interesting way to do it. It requires a lot more work up front on the part of the instructor, and it requires a lot more investment from students as well. Because if you don't watch the lectures, you come to class and everybody is talking circles around you and you can't make any contributions, and then that means that what you get out of the course will also be very limited too.
Yeah, but once you got the up front, you can just coast.
Sort of, yes, sort of.
So are you in this class, or are you like a student teacher, or
I'm a
like,
dwarf.
so you are in this class? Like
He
you're
is
a
enrolled as a student, of course, yes.
Oh, okay.
I am tired of computers. I want to say, hello, I'm Christian, I'll be your nurse. And,
Okay.
do you know what a fully cath is? You can just put the phone.
That's been in so many of those, like,
Really?
you don't have to be there.
Depending on where you're.
So yeah, with respect to attendance, I'll take attendance probably around 6 o'clock, just because I don't, like I said, I don't mind if you come in late as long as you're not disruptive. But, and so theoretically, you can kind of cheat from that too. I'm not going to be a Nazi about it, but I do have to follow the policy and enforce the policies of Columbia College. So there's some wiggle room in there. But yeah, my perspective is you're all adults. You're paying for this one way or another, either out of pocket now or over the next 30 years of your life. So I will give you the room to fail and enough rope to hang yourself with if that's what you really want to do. But I would really rather that you don't do that, and the easiest way to not do that is to come to class. But I was also the type of person that when I first got to college as a bright and shiny 18-year-old freshman, I walked into my freshman biology course, which had a required attendance policy. If you miss more than 3 days, you lose a letter grade. And so in the first 2 weeks, I proceeded to miss my 3 days, and then for the remainder of the semester, I showed up and laid my head down at a desk and slept. I was technically there, but I was also quite visibly telling the teacher how much I thought of his attempt to be my mother. So, but I don't get to make all the rules. Question?
Okay, so I've noticed with these notes, they correlate heavily to this book,
That is because they are made by the
but I mean,
publishers of the book, yes. I edit them a little bit, but yeah, they're just going to follow the book pretty straight.
part of me is like,
Why
should
did
I
I get
keep
the
this
book?
book?
Here's the thing. I can totally appreciate why you might have that picture. Here's the thing. I use these slides to keep me on topic because as probably is already apparent, if I don't have something to keep me on topic, I will end up over there, right? So the slides keep me on topic, even the ones that are repetitive, I use them to make sure that I'm staying on topic, talking about the things as we work through the book. But that does not mean that the way I explain something is going to make it stick for you. So the book is effectively another person's perspective, another knowledgeable instructor's perspective, and their attempt to explain the information to you. Now yes, the organization of the slides is going to look very similar to the book because that's how the publisher is the one that put it together, right? But that does not mean they're going to use the same terms, it does not mean they're going to use exactly the same examples, and the book is going to go into a greater depth than the slides do in explaining these concepts and differences. If you do not feel that you need it, then maybe you don't need it. Because what I'm not, if I do manage to put all of your quizzes online, then you don't even need the book to be able to answer question 4, because homework isn't going to be answer questions 4, 8, 15, 17, 29 from chapter 2. Like that's, so you don't even need it just to look up the questions. And even if you did, you could like share a book with somebody else who had it and take a picture of that page or something, right? So So I am and have always been of the opinion that your textbook is a very good reference. It is excellent as a secondary means of getting access to the material. It would be a very good thing if you read the chapter before you came to class, and that way you already have some exposure, and then I'm just going to give you another different viewpoint on it, and so it'll reinforce that information. But just rereading the chapter over and over again is not going to make this information stick in the same way that rereading these notes or even watching the recorded lectures, none of that is going to make it stick by just doing that. It doesn't matter how many times you read this information, it is not going to stick in the same way as if you take the information, synthesize it, reorganize it, and do something with it, and then that you might actually carry with you. A lot of this is going to get flushed, because that's what happens in every class. My intention is to structure the class in a way to minimize how much of that. How much benefit you get from that book is really up to you.
Yeah, because I was just thinking about like worksheets, because I feel like mathematically, like chemical equations, that's the stuff I'm really gonna have to like soak in. And
Yeah.
I've found some stuff online, but I mean.
And the book is going to give you a lot of extra problems that you could work through on top of the problem slides, right? Book's going to have even more, different ones. You could find some topical problems by just doing a Google search, I imagine. But it may be very topical. It might also be kind of like over there, and it might just confuse you because the way they're expecting you to do it isn't the same way we've described it. It really depends.
Did you find out if you have access to the online materials that?
No, because access to the online materials is more than likely, unless it's simply access to the slides, which that's a teacher's resource. But there is an online component to the book, but that's if I wanted to work through the publisher to make quizzes and things like that through their website. So I'm not doing that. So you shouldn't need any sort of online access through the publisher of the book for this course. Right, an access code. You shouldn't need that. That might give you access to other resources that maybe they have online, but I am fairly certain that that is something that you would also have to pay for, or that I would have had to enroll in and design through their website, which I have not done. So even if I got one for you, it would be heavy.
And typically to buy a new book that has
The access code, yeah. So, yeah.
They can only
All right, any questions about what we talked about so far? Shall we continue? Let's talk about temperature, something that I have sort of complained about already. So, temperature is a measure of hot or cold. It's a measure of the relative degree of heat, perhaps. We use a thermometer to measure it. We measure it in degrees Celsius, or over here in America, degrees Fahrenheit, because we're weird. But we are also very set in our ways, so there you go. What is temperature? This gets deeper than what this book is trying to keep it simple. In my opinion, too simple. What is temperature?
Measure of how fast atoms are vibrating.
Yeah, it's a measure of, well, let's get even more complex than that. What is the vibration of an atom? What type of energy is the vibration of an atom?
Electromagnetic.
No, well, sort of. You can have electromagnetic energy, but that electromagnetic energy is going to be absorbed and then converted into a very specific type of energy that we call kinetic energy. Temperature is quite literally a measure of the amount of kinetic energy an object has. And not just kinetic energy in terms of a bullet flying through the air, but also a bullet while it's sitting on the ground. Individual atoms within that bullet are going to be vibrating with a certain degree of energy. And the more vibrations they take, the faster their vibrations are, the higher their kinetic energy will be, and therefore the higher their temperature is. What is the difference between water as a gas and water as a liquid? What do you have to do to convert water as a liquid into water as a gas?
Half a calorie.
Add a crap load of energy. Way more than half a calorie. Well, depending upon how much of it we're talking about. We're going to have that in here. So, You add a lot of energy. And somehow simply the aspect of adding that energy in the form of heat gives those molecules the ability to stop holding on to each other in the form of a liquid and start being so distant from each other that they are now a gas. And what happens to that gaseous water if we cool it down by extracting energy from it? Stops vibrating so far apart from each other and condenses down into a liquid. Temperature is a measure of the average kinetic energy of an object, even while at rest, which we perceive, thanks to our senses and our mind, as hot or cold. If it has less average kinetic energy than the surface of your skin, it will feel cold. If it has more average kinetic energy than the surface of your skin, it will feel hot. We measure that difference in kinetic energy, that difference in temperature, as degrees Celsius or degree Fahrenheit or even potentially degrees Kelvin. So, like I said, that's just a tiny short rant for me because I dislike the degree of simplification of how we describe temperature in this book, but we can pretty much stick to this moving forward. I'm not going to fault someone for calling something cold, although it might make me shiver in revulsion just a little bit. I still do it. I'll still look outside when there's snow and go, wow, it's really cold out there. It's a natural thing to do. Temperature scales, Fahrenheit, Celsius, and Kelvin. We use reference points on those scales to define what the boiling point and freezing points of different molecules are. Now, we use water once again as the way in which we define these scales. The convenient thing about the Celsius scale, you'll note, water has a freezing point at exactly 0 degrees Celsius. Water has a boiling point at exactly 100 degrees Celsius. Do you think this is just convenient that we happen to pick this scale with these numbers that happens to exactly coincide with these two physical change of states of such a common and ubiquitous material that we can find all around us at any given time? No! We have this scale because we have this common and ubiquitous material that has two changes of states at very specific points. And we picked those 2 points and then subdivided everything in between by a certain arbitrary amount to give it 100 degrees of difference, which gives us a line that we can then graph what temperature is above that 100 degrees or below it. Fahrenheit, I don't even know where Fahrenheit comes from. Like, honestly, just one of those, like, I think there's a guy named Fahrenheit who invented it. I don't remember why it's 32 degrees is the freezing point. I don't know. But that's the scale that we use. Water freezes at 32 degrees Fahrenheit. It boils at 212 degrees Fahrenheit. Kelvin, the freezing point of water is 273 degrees Kelvin. You'll note that the boiling point of water is exactly 100 degrees higher than that. Kelvin is a scale that was based off of the Celsius scale that then mathematically extrapolates, if we kept getting colder, what is the absolute coldest that we can get? In other words, how much kinetic energy can we extract from an object before it literally stops moving, period? Are you moving right now? Yes. You are moving. If I was sitting in your place, I'd be tapping a foot or wiggling it or something like I can't, you may have noticed, I can't stand still. Even if I was in a coma, my atoms would still be vibrating. I would still have a temperature because of the air around me in the room where I was being stored. So therefore I would still be moving. Even if you froze me as solid as you could get, I would still be moving because the planet is rotating, it is rotating around the sun is moving around the center of the galaxy, the galaxy, and the galaxy is moving through the universe, Universe, yes. Galaxies moving through the universe, so we're all moving, like, this is why reaching absolute zero is such a really freaking hard thing to do. But mathematically, we can extrapolate where that would be, and it would be at 0 Kelvin. Getting to 0 Kelvin is not quite impossible, but it's close.
So that means it's happened.
It means that there are groups that claim that they've gotten really, really close. Like close enough that maybe we could almost be like, but you can't do this with, you will find no freezer that will keep your food at 0 degrees Kelvin.
Isn't very active in measuring it.
Yes, like attempting to define it, yes. It interacts with it in a manner that would impart, yes. So, yeah. So, anyway, those are the scales. Celsius, Kelvin, very closely related. They use the same scale. Now you'll note that there's a 180-degree difference in between the boiling and the freezing point in Fahrenheit. So 1 unit Fahrenheit is not equivalent to 1 unit Celsius, but 1 unit Celsius is equivalent to 1 unit Kelvin. Here's your exchange factor. Do you ever think that might come in handy? You know, an exchange factor. 1.8 degrees Fahrenheit to 1 degree Celsius. Where have we seen exchange factors before? Oh yeah, half of chapter 2, right? Here's the equation to convert between Fahrenheit and Celsius. This is if you want Fahrenheit and you are given Celsius, temperature in Celsius, T sub C, 1.8 times T sub C plus 32. So there is your 1.8 right there. And then we adjust our freezing point by adding 32. Because Fahrenheit doesn't freeze at 0, right? It freezes at 32. You can do a little bit of calculus and turn it into this equation right here. If you're given Fahrenheit and you want the calculus, a little bit of algebra, excuse me, to get the Celsius temperature down here. If you're unsure how to go from this equation to this one down here on the bottom, you can talk to me later and I'll show you on the board. And if you're still confused, then you should review your algebra, basic algebra a little bit. So, if you're given 21 degrees Celsius, you want temperature in Fahrenheit, how do you do it? Well, in this case, you write down the equation, you plug it in. So what, if your room is 21 degrees Celsius, what's the temperature in Fahrenheit? 1.8 times 21 plus 32. 1.8 is an exact number in the equation, 32 is an exact number in the equation, but we are given a number here with 2 significant figures. So we have an answer to the ones place here of 70 degrees. Everybody follow that? Basic algebra with the inclusion of those annoying significant figures for how far out we take it, right? What's 1.8 times 21? Somebody whip that up real quick, would you please?
$37.8.
37.8. Why is it rounded to 38?
Because it's 2 significant figures.
Right, because 21 is a measured amount, right? And it has 2 significant figures, so 37.8 becomes 38.
So I watched a YouTube video on significant figures.
Okay?
And they said that you, and I'm learning that this is maybe more of a preference, but they said that you wouldn't round until
Get to the end?
Yeah.
Right.
So either it doesn't matter.
In this case, what would happen if we rounded when we got to the end? What's 37.8 plus 32?
Well, it's 69.8, so you would round up to 70 anyways.
Right.
So it works that way though.
It works conveniently in this example. It works that way that you could either do it before or after. But yes, theoretically, the best practice would be to do the entire calculations and then round to the significant figures that you have.
Okay.
I
Any
was
question?
just thinking like, when you test on it, would that be better, test-wise? should we just solve the equation?
Let's put it this way, when I'm building the questions, that's what I'm gonna do.
Okay.
So I'm gonna do the math, and then at the end, I'm gonna round to whatever the significant figures are, if I'm asking for it.
If you are asking. for it.
Right.
It's like verbatim.
So you would have had 37.8 instead of 38.
Like on a homework question, yeah, I probably would have 69.8, or I would have 37.8, right. But the reason for that is because that comes out to a nice 37.8. What if it came out to 37.149683728? Like, how many numbers am I going to write down? How many numbers am I going to keep going? And that's one of the reasons why significant figures comes in, because at a calculator it's easy, because you just say, do this and add this and then add this, and the calculator remembers all of it. But if I was writing all this down and doing it by hand, how many digits are you going to write? Right? So, by understanding significant figures, you will know, well, I'll just write down a certain number of sig figs, and that way I don't need to write down 10 decimal points for everything, and then round at the end. Theoretically, you should get the same number.
Right.
Theoretically.
But to follow, I mean, you're the one creating questions, so I want to
Right.
follow your practice. So would your practice be,
I'm going to be using a calculator and then rounding at the end.
okay,
Right.
and then this question, say if this question, you were wanting significant figures, would it say, the typical temperature in the room is this, what is the temperature in degrees Fahrenheit, using,
With significant figures.
okay, okay.
Yeah, I'm gonna tell you. Or it's gonna be multiple choice, and the answers will be 70, 72, 16, and 12.
Okay.
Right,
I
and
just
so,
don't want
like-
anything that's like 69.8 or 70.
Right,
Right.
right. That I'm not gonna do that.
Okay.
That specifically is, and if I ever do that, call me on it, and I'll give everybody the point back.
Okay.
Because that I'm not trying to screw with you. Because, like, if I want to ask, do you understand significant figures, I will tell you. If I don't care, then I won't mention it, and it should be obvious in the answer that I'm not, that I don't care.
Okay.
But I'm not going to be trying to trick you just to make you get it wrong because you didn't use significant figures when you should have. Because theoretically, you should always use significant figures. But, does that answer your question?
Yes,
Perfect
yes.
world.
I just wanted to suggest a learning resource. A lot of YouTube videos can be very hit and miss. If you want consistency, fantastic pedagogy, and
I use Khan Academy.
Khan
There we
Academy is
go.
good.
Yeah, that's the one.
Yeah.
introduction of game theory, and yeah, incentive
There's
positions.
another one by Brian Greene that I don't remember the name of, but he has a really good educational series too. But yeah, like, anybody can make a YouTube video. So,
No, I know.
you do have to be a little careful. But there are a lot of resources out there. And this is what I mean by multiple perspectives, like what's the value of the book. If I explain something and you're like, I don't get it, and you read the book, like, I still don't get it, and then you look at a YouTube video and you're like, oh, well that made sense because he said blah 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 blah. Like, well, I thought I said that too, but evidently I didn't. Like like I said, when I was in whatever grade it is you learn fractions, I could not figure out fractions, no matter how many ways the teacher tried to explain it to me, until another kid in my class took me to the chalkboard and did something, and in 5 minutes it just clicked and never needed help with fractions again. But for a little while there, it was like, I don't understand, you're speaking German. So, like, finding someone who speaks your language. If I don't, maybe the book does. If the book doesn't, maybe I do. If neither of us do, maybe somebody online does. Kelvin. Negative 273 degrees Kelvin is absolute zero. We represent it as 0 K. There's no symbol in front of it, so it's not degrees Celsius, it's just K. Or negative 273 degrees Celsius, excuse me. Which means that there is no negative temperatures in Kelvin. There's no such thing as negative 12 Kelvin. You cannot go below 0 in Kelvin. 273 Kelvin is equal to 0 degrees Celsius. So if you need to do a conversion factor, it's just Kelvin temperature is your Celsius temperature plus 273. Easy peasy. Comparison of temperatures. The sun, let's assume we're talking about at the surface where we can actually measure it, because last time I checked we haven't been able to get, a thermometer down deep into the subsurface of the sun. So we've got almost 10,000 degrees Fahrenheit, 5,500 degrees Celsius. Hot oven, 450 versus 232. Water boils at 212 versus 100. A high fever, 104. That's like bordering on life-threatening fever, 104. 40 degrees Celsius. This is why if you know someone from Europe and you tell them how hot it is, if they haven't been here in a while, they might look at you like you're insane. Because if you said, oh, it's going to be hot tomorrow, it's going to get all up to 72, they're like, are you kidding me? Like, when they're looking outside and going, 40 degrees, wow, that's really hot. Like, you tell them it's going to be 70 and like, oh my God, there's a bacon egg on the sidewalk. 37 degrees Celsius. There's a lot of scientific reading if you look around at it. They'll talk about water baths at 37 degrees Celsius. Have you ever wondered why? That's why. We culture things at human body temperature because, well, when we care about things that are affecting the human body, those things have tended to evolve to grow really well at 37 degrees Celsius inside the human body. Because that's the temperature that our body actively spends a buttload of energy trying to stay at, no matter what the temperature is outside, above, or below it. Water freezes. A northern winter versus a Missouri winter. I mean, those are, I'll grant you it's a little bit, we never really got to negative 66 degrees Fahrenheit this winter. Liquid nitrogen, negative 346 degrees Fahrenheit, that's a fun one. Negative 210 degrees Celsius. Liquid nitrogen's really cold, yo. You guys ever got to play with liquid nitrogen? It's neat. You ever dunked your hand in it? Don't dunk your hand in liquid nitrogen.
Are you talking about dry ice?
No, I'm talking about liquid nitrogen. Dry ice is another fun one though, but different.
He's talking about dipping this and then dropping it so it will shatter.
Theoretically, do not do this. Theoretically, you could, if you had a large enough container of liquid nitrogen, you could take your hand and just go bloop and pull it back out, and you'd be fine. Your hand would be cold, but I don't mean like frozen solid cold. It'd just be like, whoop. And the reason for that is because as you dip your hand into the liquid nitrogen, your hand will boil the nitrogen so fast that it will form a pocket of gas around your hand, so the liquid nitrogen never touches it. And so your hand is surrounded by really cold nitrogen gas. Don't try this, because you leave your hand in that liquid nitrogen for a split second too long, and that pocket goes away, and now we're talking about bad stuff.
Yeah, it's like when you see people doing videos where they're smelting metal and they're doing this.
Right, yeah.
Their bare hand going in it, it's the same.
Right, it's the same idea. So it's a neat thing, but liquid nitrogen liquefies at negative 210 degrees Celsius. Your hand is around 23 degrees Celsius. There's a 200 plus degree difference there. Your hand is a lot hotter, has a lot more kinetic energy, which means that when you stick your hand into that liquid nitrogen, it is going to lose a lot of heat very quickly and boil the liquid nitrogen very quickly into gaseous nitrogen, which is still really cold. Which is why I once again reiterate, this is hypothetically a thing you could do. I do not advise doing it. Instead, take that banana and do the same thing. Go, don't, see look, it's not solid! And then go, I'll admit to me doing something really bad. I like Mountain Dews. When I ran a molecular genetics lab for a while, I had a big dewar of liquid nitrogen. We filled it every week because we had a whole bunch of cells that we needed to keep frozen. Like, frozen. Like, negative 210 degrees Celsius frozen. I would frequently get sodas, and it's cheaper to buy them from Walmart in the 6-pack than it is to get them at the gas station, but then they're warm! So I might have put on a glove and like half dunk my soda into liquid nitrogen just to chill it.
every day.
For like 10 years. So, it's way too much soda, but still, it's fine.
My ex-wife liked to tell the story of a teacher who put a racquetball and then chucked it against the wall, thinking it would shatter. Well, of course it did it. It went right through the wall. Because it was no longer a racquetball, it was a solid object.
Right, yeah. Yeah.
You know, so.
A solid rubber ball. Frozen. Yeah, that's a rock now. That's not a blue ball, it's a rock. Anyway, body temperature is about 41 degrees C. Get hyperthermia above 41